All right, here's example 1 from class 21. I'm doing problem 1689 here. And we're going to do this. This is a constrained motion, and what it's made up of is these two slender bars. We're going to pretend like they're not rectangles, but they're just very slender bars. There actually would be like an overlapping part of this, like right there, or we could cut it off right here. But we're just going to pretend like there is no overlap, and these are slender, and there's 1 foot and 2 feet long, and they're 2 pounds and 4 pounds weight. And at the moment, they have a 10 radian per second angular velocity, right? So we don't quite know what direction that's going to be, but it does have an omega right in there. And we're going to take a look at it when theta is equal to 0. And we want to determine the components of the reaction forces that are placed onto this. So some of the housekeeping to get rid of here is to get the mass moment of inertia of the whole piece about that point C. Right, so I will draw this and say, well, here's the center of part BC, and right here is the center of part AB. But we want it to be about C is where we would like to draw this. So we want to find IC, and we do that by combining IAB about its centroid and moving AB from this spot right here and moving it up. Let's see, I'll use a darker green. No, I guess I'll use a lighter green. Yeah. And moving it up this distance right there, and we will call that distance, I decided to call it ABC. Doesn't make any DABC. So this is going to be DABC squared, and then we're also going to have the other part, IBC, about its centroid, but we also need to use the parallel axis theorem and move that from right up there to C, and that right there is just going to be the length of BC over 2 that we're moving it, and make sure that we square it. All right, so one thing that we don't have as part of that is this distance DABC. So we'll write that out as DABC is equal to, well, we could take the square root, but let's just take it squared, okay? So then we don't have to take the square root. So that's going to be this distance squared plus this distance squared. So it turns out to be 0.5, I think. Let's see, I wrote that, yep. 0.5 squared plus 2 squared. And if we were to get that, we get 4.25 feet squared. That makes sense. Okay. So marching through, filling stuff out right here, we have 1/12 mass of AB, which AB is going to be 2 pounds, 32.2, and the length of it is 2. Sorry, no, the length of it is 1. Excuse me. We're taking a look at this guy right here first. 1 squared plus the mass times the distance that it's moving squared, right? Which this is already squared, so we just have to put the value in there. We saved a little tiny bit of work right there. And we take 1/12 the mass of BC, which is 4. That's 32.2, and its length is 2. And now we want the mass again, 4 divided by 32.2 of link BC, and then the length divided by 2. So that's going to be 2 divided by 2. We could do that in our heads probably. 0.435 4. So why am I stuck on that number? 4, 7, 8. And the units of these are slug feet square. Okay. Something else I might want from the geometry and want to use it later is to find this angle right there, the angle that is formed by this distance and the horizontal. That's going to be the inverse tangent of the rise, which is 2, divided by the run, which is 0.5, and we end up with a 75.96 degrees. And maybe I'm also going to probably want to know what DABC actually is. So I take the square root of 4.25, and I end up getting 2.0616 feet. Okay, we're ready to do the kinetics right now. Actually, we could go ahead. No, let's do the kinetics. Okay, so I'm going to take my Newton's N2L here for the Newton's second law. I'll write out my FBD. All right, this thing's getting out of hand. And it's going to be equal to my IBD. We'll define our coordinate system and apply our reactions. So it's going to be RCY and RCX. I'm going to put on my gravity. We'll have the weight of AB, and also, I'm a little crazy, weight of BC. And now over on this side, we can say that the angular acceleration, so we can have I, C, angular acceleration. Now, I kind of prefer to leave it this way, but because we want to actually get the reactions, we also do need to add in the other accelerations, right? So if we were only doing the sum of the moments, we could probably leave it this way, and that would be a better probably representation for us to not cause confusion. But we also want to have the what the translational aspects of it are going to be. So we got mass times the acceleration of BC in the, this will be the normal direction is what I'm representing there. So that's going to be the vertical thing, arrow that you see. And then mass times the acceleration of BC in the tangential. That's with that downward arrow. Well, I don't show that downward. It's an upward arrow. Oh, no, that's this one right here. I'm sorry. I misspoke. Okay. And by the way, that should be a mass of BC and mass of BC. And then we also have the acceleration here of this point, and it's best for us to maybe align it so it is actually pointing in the direction of its acceleration. So that's the mass of AB times the acceleration of AB in the that's the tangential, and then it's going to be hard to fit it in here. Mass of AB times the acceleration. Ooh, boy, the little guy went crazy there. Of AB in the normal direction. That's a little n right there. It's hard to see. Okay. So if I take the sum of the moments, let me see. I'll draw it up here. The sum of the moments and we about C, and we can use IC alpha, right? We're allowed to use that because this is the special circumstances where it is a constrained about a plane. So all we have going on here is in the left-hand side is going to be the weight of AB, and it's going to act through LAB over 2, right? So just weight AB, LAB over 2, and it's going to be positive because it's counterclockwise, and that's going to be equal to IC alpha, right? And we don't want to, and we don't need to put any other things over onto that side. We want to be careful here that we don't double dip. That's sort of the hazard of this type of problem right here, of this situation, is double dipping. That we were to already have moved that I to the moment of inertia to that point C, and then also take the effective moments. You don't do both of those things, one or the other. So we take the 2 pounds that are active right there, and then we take our L over LAB, so that's going to be 1 over 2, right? We can do that, it's easy enough. And then we have the 0.43478 times alpha, and we're able to find that alpha is going to be equal to 2.300 radians per second squared. And we got positive, so that's definitely there. That's going to be part of the answer. Now we want to go and do some kinetics. So hopefully I've left enough space for myself. So we do some kinetics up here. Kinematics. I said kinetics and I meant kinematics. Kinematics. Well, the thing is, there's a little lag going on here. So let's see. I'll start off with AB, and that in the normal direction, all we need is get the omega squared, right, and then the distance of that is away. So remember, that's going to be this distance, that D, A, B, C, right? So if you plug those in there, we're given that it's 10 radians per second is the omega of the thing. So squared, I wrote an equal sign, and I didn't mean to. Times are 2.0616. And we could do that math easy enough. 206 point, I guess I go 2 if I want to, right? And that's going to be feet per second. Oh, feet per second squared. And then we have the acceleration of AB tangentially. And that's going to be alpha times DABC. We just found out alpha. 2.0616. Boy, there's a little lag going on here. I wonder if the computer's bogged down. Probably, and that's 4.742 feet per second squared. Look at that. I wrote that. Is it still good? Oh, that took that long to pop up. That's not good. We get the acceleration of BC in the normal direction. Once again, it's omega squared, but now it's going to be LBC over 2, right? Because we're taking it right around here at that point. And so it's 10 squared, but now 2 over 2. We can do that in our heads probably and get 100 feet per second squared. Look at that. That's a big delay. And then we have the alpha LBC over 2. Maybe I should turn the computer off and start it up again. I'll do that. 2.300, 2 over 2. We get 2.300 feet per second squared. Wow, come on. Yeah, this thing's exhausted. I've been pushing the computer hard. All right, so we've worked out what all the accelerations are. Now if we want the reaction forces, what we need a little break from the computers. What we need the sum of the forces in the x direction is equal to mass times acceleration in the x direction. And so looking on the left-hand side, the only forces in the x direction are going to be RCX, right? Nothing else there, so that's going to be the left-hand side. On the right-hand side, we're going to have the mass of BC times acceleration of BC in the tangential direction. Easy enough, and that's positive, right? Because this guy's right here is pointing to the right. But now we have to break this other guy into parts. Right here, this guy right here, and in here, right? So that's going to be this angle right here, that theta I described up above, and right here is also theta in the way that I've drawn it. So we will say, let's take a look at the, I think I went the tangential one first. So that's going to be, it's in a positive x direction, so that's going to be AB, MAB, times the acceleration of AB tangential, but it's going to be the sine of theta, right? Because that ends up being the in this direction right here, opposite from the angle. And then we also take a look at the normal direction, and so that's going to be plus MAB times the acceleration of AB in the normal direction. But now we're going to go, it's going to be the cosine, right? Because it's going to be this leg right here, and that's going to be adjacent. So the cosine of theta. So we're going to plug some numbers in here. For the mass of BC, that's the big one, right? So that's going to be 4 pounds divided by 32.2. And BC tangent is 2.300, right? And then we have mass of AB, which is going to be 2 divided by 32.2. And the acceleration of AB in the tangential direction is 4.742. And taking the sine of our 75.96. Okay. And then last part, look at that. All right, so we're going to get 2 divided by 32.2 ABN, which is our 206.2, and then the cosine of 75.96. And we'll go to the next page. What we end up finding is our CX is therefore equal to 3.678. Okay, so now we have the response back again. Maybe I just drew too much stuff on that one page. And so that's part of the answer. So now we also want the sum of the forces in the y direction equals mass times acceleration in the y direction. Positive being upwards. And what we find, we get RCY, and that's on the right hand side. Whoops, no. We also have the weights downwards of both of them. So that's going to be minus 2 and minus 4. And then we go through the rest of the stuff, right? It's going to be the mass. Let's just write the thing out, right? So we have the mass of BC is 4 over 32.2. And the acceleration of it is going to be upwards. So it's going to be positive and of BC. And that's going to be ABCN. So BCN, so that's 100, right? So it's going to be 100, right? And then we also have the other components of the thing. And so we're going to see that we have in tangential direction is actually going to be negative MAB times ABT. And AB in the tangential direction is 4.742. So it's going to be minus 2 over 32.2 and the 4.742. And what direction is that going to be? That is going to be the cosine, right? Because it's going to be this guy right there. The cosine of 75.96. And lastly, we'll take a look at the normal direction of AB, and that's going upwards. So that's positive, and its acceleration in the normal direction is 206.2, and also we know that we're going to use a sine. So if we could remember all those things, it's positive 232.2. It's going to be the 206, where'd you go, 6.2, and then we're also going to have the sine of 75.96. And we get all that, and we get RCY is going to be 30.77 pounds. And it's going to be upwards. Even though the weight, no, that's fine. No, okay. Yeah, it's going to be upwards. Oh boy, there's a big, a little more. So anyway, that was the example problem of 1689. And that's from the 12th edition. So while we're here, let's, I'm going to keep it. Let me take a look at what the solution manual is. And I don't mind showing the solution manuals too. So let's see what method that they used right here. So this is good. It's good to see different approaches. Here's the Johnston, and I don't know if I have the 12th. I think I have the 14th. So this might not be the same solution right here. That would be a damn shame if it was. Let's take a look at the 11th. Maybe the 11th is chance. I've written down that this is the 12th edition. So let's see. Let's take a look and see. It might not be the same numbering right here, and they might have changed the numbers from one year to another. They do that just to be tricky. And of course, our OneDrive is deciding to go slowly. That's not surprising. Okay, so let's see. This is probably down to problem 89. Okay, so 2, 4, 10, sure enough. Okay, and you'll still notice, let's see, as we're walking through this right here, they do all the same things. They get the mass moment of inertia of the individual parts, there should be a line over this BC, because you could tell that that's going to be about the center, both of those. And they get the relationships between the kinematics right here, and they draw these, and they decided to call beta. All right, so that's what they call it here. And they used 0.5 over 2 instead of what we used was 2 over 0.5. So they got the complementary angle of our 75.96. And then they did, here they've drawn, this is the FBD and the IBD. You see that they've drawn them over to the side of that. They just wanted to save room, and they drew them by hand. But these are all the same things. But by the way, they didn't transfer the moment of inertia up to point C. So what they're doing is, as you'll see, like in the same notation that I've used before, they have used, see, I'll write in this guy. You'll notice that they wrote out, they didn't use the same equation as we did. So this was an alternate method. But what they end up doing right here, you'll notice, is if you were, when you pull out that alpha that's right in here out of the thing, right? So they do this stuff on the right hand side out, and then they combine right here. That's the parallel axis theorem, and that's the parallel axis theorem. So they end up doing the same thing that we did, and you see that they got the same answer, 2.3. And then they proceed to and then they're using the same nomenclature here, where they're saying in the x direction they have the effective, and they got the same thing as me, yes, 3.677, and then in the y direction, right, that we get 30.773. And they did all of the same things. So you'll see that we get the same answer. They also decided to go magnitude and direction with their result and with the quadrant. So I thought maybe I would just point out to you the methods that I use are consistent with some of the presentation, even if you don't always see it in the book. But that's where I got it from. And let's see what we have here. 27 minutes. That's a long time it was a longish problem though. And I think we're good here. We don't need to do any guitar stuff today. So, great. Thanks a lot.